Hello and welcome to my channel. Hey Arctic, nice to see you on board today, mate. Right, as Arctic noticed, I'm actually going to continue on the discussion he started where he debunked the idea that the speed of a vessel in the water is somehow attached to these magical charts that they believe in a different group of people. In case you're wondering what the glove's for, I've got a little pad here I can write on, so it allows me to slip the hand a bit easier. So let's go and have a quick look at the whiteboard, because I set this up purely and simply so we can have a very quick and simple list to work from. Now, the earliest means possible for doing this, you're going to love this. It was a very, very simple process, and I know Arctic's going to love this one. It was nothing more than a rope tied to a log with a series of knots at reasonably equal intervals. Funnily enough, all the sailors did was threw over the side, waited for 30 seconds or some count time, and they come up with the number of knots that slip through their hands, and of course there is our measurement of speed, knots. Wasn't a great standard, not everybody could use it, but basically that's how they did it. Now we need to turn our attention to some of the more modern things, because there's plenty of those, and I've only put down 4 very straightforward ones. So let's just start with a little bit of a clean up on my board, because it does get very cluttered very quickly on here. Okay, now the pitometer is a really interesting term, because it's not immediately obvious what a pitometer means. So a little bit of research on my behalf, because I admit I have not heard the name before. And I've got an aviation background, and when I saw what it did, I went, oh, okay, this is the equivalent of a pitot-static system used in aviation. The only difference is that both sides of it work with water instead. So let's just go and have a quick look at a browser view of this very thing here. This is a basic outline of one using a submarine. You basically had a pair of probes that went out in the water and came back to a device called a manometer. Manometers just give you pressure differentials, and all they do is they work out the speed exactly the same way they do with aircraft. Pressure being applied because you're moving versus the static pressure which is just around you. The difference between those two is how you can get the speed. The technology is very, very simple, and there's the little diagram they've produced. Let me go to the right spot, sorry about that. The manometer side of this is actually all I need to do. I'm just going to blow this up a bit in size, because I know that these diagrams can be a little bit hard to read. Now hopefully everyone can see that that looks correct. Yep. What you're seeing here is the basics of the manometer. They used to use mercury, because mercury was quite heavy and it gave you some inertia in measurements, and it's simply that difference in pressure. That's all they're looking for. And that difference in pressure is a result of moving through a fluid, and whether it's air or water, it doesn't really matter. That's the whole point. So all we have to do to calibrate this is have a pressure device that can apply pressure to that in either air or water, and check that the manometer reading agrees with the formulas, because that's how it's done. And I do love the way they've done this. It's just a very simple formula. The difference between the two, you get a dynamic, and you can use the appropriate equation, you can actually get your velocity out of that. And that's really, really simple. Now the other alternatives, some boats now I've seen have a little plastic impeller. A couple of things about the impeller which I think are very important and would make a lot more sense if we just drew a very quick diagram of what the impeller should look like. The vane impeller is simply a little round wheel with some blades on it. That's the basics of the vane impeller. And it doesn't all stick out. They only allow a certain amount of the vane impeller to actually protrude into the water, and as the water comes along it strikes it this way. Now something that's really important, if we look at that vane impeller this way, with its axis running this way, you'll actually notice some of the newer ones, they actually have like a V shape on them. And this is really important. You want the impeller to work when the water is pushing in that direction. If the water goes sideways, you want that to have the minimum possible effect. So having the V-shaped impeller, it will push on this one and then hit the next one and push in the opposite direction. So this one would push it that way. Sorry, it's created on there, doesn't it? It's created very quickly. And when it hits the other impeller, it's now pushing in the opposite direction. What you get is balancing out of all of the forces, and the vane impeller simply doesn't run unless you are running forward. Now, in Arctic's last video, I saw a comment and it just made me think there's just no common sense here. The fact is that you cannot calibrate these to the charts, because every time you change latitude you'd be taking these things off and you'd be readjusting everything, and it doesn't seem to be happening. There's a race in Australia, and again, just a very quick diagram. We've got Carpentaria down the east coast of Australia, all the way down underneath, and a little thing down there we call Tasmania, and they leave from a place called Sydney, and they are going through lines of latitude all the way down, and you cannot possibly be running that race all that distance without pulling these devices out and recalibrating them to get them to match the charts. It seems to me that they've never really thought about this. Now, this is probably the most common one that you will find out there. There are a couple of electronic ones, and I'm not going in that deep. The whole idea is just to do a short video, explain how these things work and explain how they calibrate. And the GPS speed is pretty straightforward. All it is you've got your first position P1, you've got your second position P2, and you simply use your hover sign to get a great circle. And pardon my terrible handwriting. Let's get rid of all this. To get your distance based on the great circle. If you know what time that one was taken and what time that one was taken, and then you've got to calculate distance, you put your distance back into your delta time, and what have you got? You've just picked up speed. That's it. As long as the GPS positions and times are accurate, that will have accuracy as well. I think that one's pretty straightforward. It wasn't a really hard exercise to go into to talk about that one. But the electronic ones, I think they confuse some people because they're kind of not really sure. They think, oh, maybe it's like this, maybe it's like that. And coming from an aviation background, I can tell you right now, it's not what you think. In fact, my aviation experience goes back to really early, simple things, and I'm always proud to hold up this one because this is an altimeter. It is that old. It doesn't have any general electronics in it. It's an old-fashioned anemometer inside, and it actually has little capsules that squeeze and release and goes through some sectors and turns into a rotating display on there. If you didn't have that, you simply wouldn't be able to do what you're doing. The other little instrument I got my hands on, that's an airspeed indicator, and they always have two holes in the back of them. This is an example of a manometer at work measuring the speed of the aircraft through the sky. And it's based completely on the tube that sticks out, the pitot tube, and that comes back to a pitometer there. And that's pretty much it. Right. Ultrasonic Doppler is a little bit different. If you're not used to working with the idea of ultrasonics, basically, hull of a ship, a couple of choices. There are some which look through the hull, there are some which actually penetrate the hull. Either way, when you send an ultrasonic beam down into the water, you can actually detect the water pushing that beam around, and you can tell when you get back your delta frequency difference, and from that you can work out your actual speed, because the frequency is directly proportional to the velocity that you are travelling at through the water. Okay, I think I've covered off most of what I want. Arctic, have you got any comments you want to make? Okay, cool. kind of feel like I've covered it off. I really did just want to talk about this in very simplistic terms, just to give people a good bit of an overview about it. I hope I've got the point across. If you are not believing this stuff works, go out and make yourself a rope-based system, tie knots and run it that way. And see if you can measure speed. Oh, there's one other little thing I think I should bring up, and it's probably worth having a look at this one. They actually have a diagram on, where did I see it? This one. This is a submarine log, petometer log, and if you just scroll down, they show you how they measure the 1 mile. The 1 mile is physically measured by a bunch of markers. They check when you pass a point that you've got land-based 1 mile, and they just run it up and down course, come around, and they just keep going, and the course gets longer and longer, so you end up running through here multiple times, and then they show you the calculations and how they worked it all out. It's actually quite interesting to see them do this. Calibration of instrumentation like this is not easy. Another example of something that's not easy to do, an aircraft compass swing, and I know I'm getting a little bit off the topic here, but if we just have a quick look, your average aircraft compass swing is actually done by taking your aircraft out to a space that is surveyed for the purpose of ensuring that when your aircraft is lined up a certain way, I'm having good fun with this tonight, that the compass will tell you if you're going facing north or not. Basically the aircraft then is turned to face a different direction, and there are people with theodolites looking at this. They actually check that that line running down an aircraft is correctly set up, and they can tell the pilot that you are facing true north, and if the pilot reads his compass, and he'll see he's got 10 degrees when he's actually facing north. That's how they do these things. So compass swings are really important. Aircraft especially, they move a lot faster than boats most of the time, and that's one of the things you look at. Okay, just let me clean up my board. Okay folks, I think I kind of feel like I'm done, because there's always an extra little thing. Right, but even your boat compass has to have a compass swing done on the same reason. The boat contains metal components, and some of those are ferromagnetic. If they're ferromagnetic, they will generate a change in magnetic field, so the compass swing actually checks the compass when the boat's facing a certain direction. I'm going to do another one. Thanks mate. Right, I'm going to do another video. I'm going to talk about magnetic declination, because magnetic declination is another thing that's been brought up in some of those videos, and to be quite frank, I'm a bit concerned that the information being presented is not correct, because you said that somewhere between South America and Australia it was like minus 50 degrees, but I just double checked after I saw that, and the declination in Perth is about 0 degrees, while over in Sydney it's around 12 degrees. I think we've got some anomalies between what people are saying and what's actually happening. Okay, Arctic, so good to have you on board tonight. I really appreciate your company, and thanks for the little bit of feedback. Just let me know how things are going. With that, I'm out of here guys. Have a good night. If you liked it, please subscribe, click the like button, and we'll come back in a few days with another video for everyone to work with.